Now let's take a second example. This example is also very simple. It refers to our choice of the system itself. Now, this often happens when we have more than one object undergoing the same acceleration. Like in this case, we got a horizontal table, frictionless. There are two boxes, number 1 and number 2, and they're against one another. You use a force F, a given force, to push on box 1, and then box 2 is against it, so that both will move together with a certain acceleration. What is that acceleration equal to? Well, it's a very simple problem. So I'm sure the solution is not that hard to obtain, but the thing is, I want to use this example to show you how to choose our system wisely. In this case, we have a choice. We can either split object 1 and 2 apart so that they become separate systems, system 1, system 2, or we can combine them into the same system because after all, they have the same exact acceleration. Okay, let's look at the pros and cons of separating them versus combining them. Now, if I were to separate 1 and 2, okay, then I need to draw a separate free body diagram for object 1 and object 2. And here is a free body diagram for object 1. Okay, object 1, free body diagram. You have a force, that force applied on it, right? And of course, object 2 also pushes object 1 back with a force N, normal force. I don't know what it is. I do know what F is, but I don't know what N is. Okay, that is what happens horizontally. Vertically, there is a pair of forces. You got M1G, and you got another normal force. Let's call it N1. Okay, N1, that's from the table. Of course, these two forces cancel. Why? Because the thing doesn't move up and down at all. So we don't have to worry about these two forces. Now, let's look at object 2. Object 2, let's draw a free body diagram, okay? Let me ask you, if I consider object 2 alone as a system, should I take that F into consideration when I draw the free body diagram? Well, the answer depends on whether this force F is acted upon this system directly. Is it? No, it is not. It is acted upon F1, object 1 directly. Okay, so which force is applied to this system 2 directly? There is only one horizontal force, and that is the force, normal force between object 1 and object 2. That's N, right? When object 2 pushes 1 back with a force N, by reaction, object 1 pushes object 2 forward by a force N. You see, that N. These two N's are a pair of action and reaction, but they're exerted on different objects. Okay, of course, you also have M2G down and N2 from the table up. Again, I don't care about these two forces because they cancel out anyways. Now, what do I do next? The coordinate system is so obvious. There is no second choice, really. If you want to solve this problem, really simple. It's just horizontal and vertical because the thing moves horizontally. Both of them, actually. Okay, so let's write down Newton's second law in a horizontal direction for this guy first. I choose forward direction is positive, then I have F minus N equals M1 A. I mean, I should have written A1 here, but A1 and A2 are the same anyway, so let's just call it A. Okay. Now, secondly, let's look at this guy. For this guy, horizontally, there is only one force N. N equals M2G. I'm sorry, M2A. That's it. Same A. My job is to find A. There are two unknowns, A and N, right? How does one get rid of N to solve for A? The simplest thing to do is simply add them up. Okay? If I add them up, then I get F equals M1A plus M2A. That is M1 plus M2 times A. And there we go. We found A. Okay? We can find A easily. F over M1 plus M2. That was when we separated those two blocks into different systems. In doing so, we can write down an equation for each one of them. There will be a pair of forces, action and reaction, but they're exerted on different objects. Okay? How do we eliminate that? By adding the equations up. That's what we did. But, you know, we don't have to separate these two boxes. We can just put them together as into the same system. And if we did that, then what happens is that we have a whole object, which is 1 plus 2. Okay? It consists of both of them. Let's draw a free body diagram for that guy. Do I still have to consider the force between 1 and 2? Well, not anymore. By definition, the force between 1 and 2 is from one part of the system to another part of the system, and that is by definition internal force. We never have to worry about internal forces because they cancel out anyways. Okay, the only horizontal external force is F, right? That's it. And what's the mass of this whole system? m1 plus m2. So how should I write down Newton's second law in the horizontal direction? Of course, there's vertical direct force. I don't even bother to draw. Force equals total mass times the acceleration. Total mass is m1 plus m2. That's it. See? Same exact thing. So, what did we learn from this problem? How do we generalize what we learned? Well, to generalize, if a system is made of various parts, you have a choice of taking them apart into separate systems or combining them into the same system. Okay, which one is better? That depends on what we're looking for. If we're looking for just the acceleration of the whole thing, then typically it is better to combine them into the same system. What's the advantage? We don't have to bother with the force between them, because by combining different parts into the same system, we have turned these forces into internal forces, okay? Because that's from one part of the system to another part of the system. Internal forces never appear in our equations because they're eliminated by Newton's third law. So that is the advantage of putting various parts into the same system. That is how you eliminate internal force to get the acceleration directly. But what is the con? Well, that was the pro. What is the con? The con is for the very same reason. You know, you don't have to worry about internal force. But on the other hand, what if we do want to know what n is? Can we obtain n by simply combining these things together? No, because you can never solve an internal force. Okay, you can only find external force. So what if we do want to know n, then we have no choice but to separate them. That's the only way we can find n. In fact, we can find n easily once we know what f is. And once we know a is, right? A is f over m1 plus m2. You can plug into either one of them, you can find n. Okay, so n equals m2 times a, which is equal to f over m1 plus m2. That is obtained by separating them. Okay, so that's the technique. Now, I also want to say that it is possible to use a mixed approach. For example, if I want to find a and n for this system, okay, we can take a mixed approach. That is, let us first combine these two objects together so that we can have this simple equation to find a. Now, once we find a, then we can, in order to find n, let us take either object 1 or object 2 out of it, out of the rest of the system, and call it a single system, say object 2. See, we already know what a is, right? Then we can solve for n by applying Newton's second law separately to object 2. That is called a mixed approach, because we combine the system first together to find a, and then, in order to find an otherwise internal force, we isolate part of the system out to apply Newton's second law to it. Okay, so that is possible. It is possible to combine the system and separate them in the same problem. Okay, before we move on with more problems, let's take a look at another class of common forces, the force of friction. We're looking at a simple kind of friction, that is, friction between a solid surface and another solid surface. Say, for example, when you drive your car, the tire is made of rubber, and if you drive on a concrete, there is a force of friction between the concrete and the rubber tires. That is an example of friction. Solid surface on solid surface. When you look at forces of friction between two solid surfaces, we can further classify it into two categories, static and kinetic. What is the difference? Well, if the two surfaces are sliding against one another, there is relative motion between them, that is, we call it kinetic friction. Okay, if sliding has not taken place yet, we call it static friction. Okay, so that's when there is no relative motion between the two surfaces in question. We call it static friction. Let's take a look at static friction. Suppose I have a rough surface with a heavy box sitting on it. Okay, and I'm going to give a force to push it. And since the surface is so rough, nothing happens. The box stays put. What did I tell you? The net force on the box must remain zero, which means whatever force I apply, okay, there is a backward force which holds the box steady so that the box doesn't move. That is a friction. It's static friction because the box has not started to slide against the surface against the ground. Okay, so that doesn't work. So let me apply a greater amount of force, and it still does not slide. That means the static friction keeps on increasing. It always matches the effort that I make. So I try even harder and even harder. Okay, so at some point the force applied is so large that the thing finally starts to move. So what did that tell you? The static friction, as far as the magnitude is concerned, the static friction can vary between 0 up to a certain maximum value. And if you apply a force which exceeds that maximum value, you can overcome it and the thing will start to move and you go to kinetic friction. Okay, so the magnitude of the static friction, Fs, Fs means static, can vary between 0 and a maximum value, Fs maximum. Okay, what is this maximum value equal to? Well, common sense tells us it depends, for example, for this box, depends on how heavy the box is, right? But it doesn't have to be a horizontal surface. You can have inclined surfaces, you can have friction. So in general, it is not the weight, but rather how much force, how much normal force there is between two surfaces. Say on the horizontal table, the normal force is actually equal to the weight, okay, of the box. But in general, you have a lot of contact normal force between the two surfaces, then you have to overcome a greater static friction. That's one thing. So we conclude, even though we didn't quite derive that, but experimentally it makes sense that Fs maximum, the maximum available amount of static friction, is proportional to n, the normal force. But that doesn't tell you the whole story. It also depends on the surface conditions, right? If you push it on ice, that's much easier than push it on a rough, cement surface. Okay, so obviously the surface conditions also matter. How do we denote the surface conditions? Well, depending on the condition of both surfaces, the maximum static friction can change. So I'm going to use a coefficient to help me identify that. We call this number mu. S. S again means static. Mu s is called the coefficient of static friction. Okay, coefficient of static friction. It is a dimensionless number such that the maximum amount of available static friction between these two surfaces equals mu s times n. Okay? This is from experiment, mu s times n. Mu s is a dimensionless number which usually is less than 1. What is it equal to? Well, that depends on the surface conditions, the condition of both surfaces. There is a table in the textbook that tells you some values of common combinations of materials. Now, what about the kinetic friction? We all have the experience that if you want to push something really heavy, it takes a lot of effort, right, to start moving. That is to overcome maximum static friction. But once the things start to move, things become much easier, becomes lighter. So that means there is kinetic friction when the thing is already when the two pieces are already sliding against one another. But kinetic friction usually is less than the maximum value of static friction. Okay, and it turns out, if we look at two solid surfaces, then the kinetic friction is rather simple for most surfaces, and that is, it is not a complicated matter that depends on the area of contact and the shape and size of the object. Rather, it depends only on two things. One is, again, the normal force n. The other is the contact surface conditions, what kind of materials, how rough they are. Okay. And to do that, let us introduce yet another coefficient called mu k. K means kinetic, of course, such that Fk equals mu k times n. And the fact that the kinetic friction usually is less than the maximum value of the static friction tells you the mu k is usually less than mu s. Okay, so once the things start to move, you have pretty much a constant resistance of kinetic friction, which is mu k times n. Now, it goes without saying that the direction of friction is always against the direction of motion in the case of kinetic friction. Okay. In the case of static friction, there is no motion yet, but you want to push it this way. So the object has a tendency to move forward and friction is backward, which means for the static friction, the direction is against the tendency of motion. And in kinetic friction, it is simply against the direction of actual motion. That is the force of static and kinetic friction.